Hello, we are Memphis Community University, and today we are going to be going over an overview on table free response questions on the AP Calculus exam. So let me just explain a little bit what we're doing. So for every single free response question topic on the AP exam, both A, B, and BC, so accumulation free response question, graph free response questions, table free response questions, this video right here, we've created 11 videos. One overview video, so this is going to be the overview video for table free response questions, as well as 10 videos with practice questions. So we go from difficulty 1 all the way up through difficulty 10. All of the practice questions are based off old AP exams. So in this case, we're doing table free response questions, and these are some of the most important free response questions because they appear basically every single year, both on the AB and the BC exam. Usually they appear as sort of the shared free response question on the AB and the BC exam. So they are very important. Usually they're non-calculator because you're just working with the table. And they're also not too bad. So if you know the general way of the land here, or the sort of the three main questions they ask and sort of a little bit about the miscellaneous stuff, then you should be very fine, and it should be one of your best free response questions because the math shouldn't be too hard because we're dealing with numbers in a table. So we'll be multiplying and adding numbers in a table, subtracting, dividing, but we won't have to do very complicated math in terms of integrals or derivatives because we'll be working with this table. So what we're going to do is we're going to talk about the three main questions that are asked in these table free response questions. Of course, there's usually 4 subparts, so we might not get to cover every single thing from these 3 topics, but we'll talk about some of the miscellaneous things at the end. So hopefully this entire overview video will complete and we'll talk about a wide range of these table free response questions, sort of go over everything that they might possibly ask. And then, of course, once you're done watching this, what we encourage you to do is to watch our difficulty videos as we go from difficulty 1 through 10 to sort of practice these concepts that we covered today. So the 3 main questions that they like to ask, the first one is approximating a derivative using a table. The second one is MVT or IVT, because you have a table, so it's pretty easy to employ that. And then there's a lot of questions on Riemann sums, so we're going to practice all 4 types of Riemann sums. Then what we're going to do at the very end is talk about some interpretation. So some of my students are really good at getting the math right, but they're not good at sort of explaining what the answer in the context of the question is. So we're going to talk about that. We're going to focus on units when we do that. And then finally, we have some miscellaneous questions again. When you have these table free response questions, not every single subpart of the table uses the table. You might go outside of the table, and usually when you go outside the table, that is when the free response question gets a little bit harder. So let's just start going over stuff. So again, the first thing they like to do, let me flip the page, is they like to approximate a derivative. So we're going to be careful with that. So this is usually the easiest question. Derivatives are of course, calculus slope. So approximating a derivative is usually algebra slope. So for example, let's say we want to approximate g prime of 6. Again, it's not too bad. All you do is you don't take the algebra slope because, not the algebra slope. You don't take the calculus slope because there's nothing to take the calculus slope of, the derivative. So in this case, we're approximating, so we can change it to approximate. And what you do is you just choose the number, the 2 columns where this number that you want to approximate at is in between. So in this case, it's 6 because it's right here. It's in between 4 and 8. And you're just going to do algebra slope. So it's not that bad. It's just going to be g of 13 minus g of 5. Over, sorry, not g of 13. I'm already struggling here. So let's practice again with algebra slope. So these are your t values. So those are the x values in this case. These are your y values. So I wrote g of 13. I meant g of 8, of course, minus g of 4 over 8 minus 4. And what is g of 8? Well, it's 13. And what it's 5. So I just said it was one of the easiest questions and I messed it up. So just be wary that and I'm also going in a circle here because I messed it up here. But just be careful with these questions. You're setting up questions, your division, even the easiest questions people miss, including myself. So here we have 2 here. One question that they like to ask is include units. Remember that if you have a derivative, if you're approximating a derivative or if you're finding average rate, what it's going to be is it's going to be the units you're going to divide by a time period. So notice that this unit, whatever g is, it might be some rate of water flow. This is already in gallons per second. So this approximation derivative will be in gallons per second squared. Or if you want to say gallons per second, because we started off with this unit, we divide by a time when we do our units for g prime. And that's it. Another question that they like to ask, and it's very similar, is just finding the average rate. So this question would be the same thing as finding the average rate of g over this time period. Right here. So it would be the same sort of process. You would do algebra slope, g of 8 minus g of 4 over 8 minus 4, and you would get the same number. And it would still be in 2 gallons per second squared, because while average rate and calculus instantaneous rate are different things, they're both rates, so they both share the same units. You're dividing by time. Keep in mind that average rate is usually algebra slope. That's sort of the way it goes, where instantaneous rate is usually calculus slope. So for example, we can practice again. One thing is that sometimes they like to combine Fourier response questions. So for example, sometimes while the function in the table might be something, some sort of real world situation like temperature or water flow, as we've seen, a lot of times they'll have particle motion questions where the velocity is the function on the table. If you watch our videos, about half of them, starting at difficulty 2, 4, 6, and 8, I believe, all of those are particle motion questions in the context of a table Fourier response question. We don't consider them particle motion Fourier response questions, actually, because that's usually when velocity is given. You can practice, watch our videos on those. There's a separate series, but in this case, just keep in mind that when we do this, sometimes we'll have velocity in the sign chart. So for example, they might ask something about like finding the average acceleration over t is equal to 2 to t equals 6 using this table. So again, you might not be able to tell, but this is the word acceleration. So average acceleration, again, is the same thing as average rate of velocity. So what you would be doing is you would, again, be doing algebra slope. So it would be v of 6. These are the t values, so these are your x values, really, minus v of 2 over 6 minus 2. And then v of 6, of course, is 3. V of 2 is 4. So it looks like we're going to get negative 1/4 here. So again, I don't know why I'm writing it backwards here, but that's just what I'm going to do right now. So keep in mind that, again, this units would be dividing by time. So if velocity is in meters per second, then, of course, acceleration would be in meters per second squared. So that's the quick rundown on the usual first question in a table Fourier response. Approximating the derivative. Again, what you do is you just choose the right columns, or same thing with average rate. You choose the right columns, you just do algebra slope, and be careful with units, divide by time. So the second thing that is commonly asked in in table Fourier response questions is MBT, IBT. And why is that? Well, you have a table, so it's pretty easy to show values exist in certain things like that. So keep in mind, when do you use MBT, IBT? Well, it's when you have a really weird, weirdly worded question. Sorry, I can't speak, but weirdly worded question. So for example, instead of saying find this time or find this derivative or find this integral where the answer is a number, MBT IBT questions are phrased in such a way that they're, for example, it's like, why must there exist, or show why this must happen, or why must this t be a thing at some interval. And so remember that MBT and IBT are existence theorems, and that's how you know whether to use MBT or IBT, or that it is an MBT or IBT question. Because MBT or IBT are existence theorems, so they're not going to actually find you a t value. What they do is they show you a certain t exists, whether it's about the function or the derivative. So again, when do you do MBT, IBT questions? It's when the question is worded. What's the fewest number of times this might happen? Show that this function equals this number for some x value. Why must there be a t in this time interval where this happens? So that's sort of the wording for MBT or IBT. Then when you decide whether you want to do MBT, that it is MBT or IBT, you have to decide which one you want to do, MBT or IBT. So keep in mind that IBT says that if a function value is equal to if a number is in between the y values of the function, then there's going to be an f of c equals the number. And then MBT says calculus slope equal to algebra slope somewhere in the interval. So what I tell my students is that when you're choosing between MBT or IBT, if the function matches, that's going to be probably IBT, because IBT deals with y values and not derivatives. If the function is the derivative of the function in the table, the given, then that's probably when you do MVT, because MVT deals with derivatives. It's calculus slope equals algebra slope. So let's practice this IVT and MVT question. So again, I would assume that this is IVT because the function's in the value. The given function and the want function, so the table function and this function in the question, is the same thing. So we're going to be doing IVT. Again, what you do for IVT, it's very simple. You write by IVT, and all you do is you just, intermediate value theorem, you just say that this y value is in between the y values of the interval. Just keep in mind that it's not the x values, or t values, 2 and 6. Instead, sorry, we had the wrong numbers. Let's change this to 5 instead. My apologies. Yes. Sorry, I meant 2 to 5 in both of these tables. Okay, so we're doing 2 to 5. So by IVT, why must this 2 exist? Why must there be a v of c is equal to 2? Well, 2 is in between the y values, so it's in between the y values of these two guys. Keep in mind that sometimes you have to change the interval, but if they give you a very specific interval like this, like it's not the full interval, it's only 2 to 5 and not the entire interval 2 to 6, usually you use that interval. So what we're going to say is by IVT, because this y value is in between, BTW stands for in between, v of 2, which is 4, and v of 6, which is 3, oh, not v of 6, we're doing v of 5, sorry, v of 5, which is 1. Then we actually did all the work for IVT already. All we do in IVT is show that this y value we want is in between the y values of the endpoints. So then what you do is you just conclude their sentence. So they didn't really write out a sentence, obviously, in this case, but you just basically copy down their sentence. When they say, why must there exist something? Your conclusion is, there must exist something by IVT. So then v of c equals 2 for some c and in between 2 and 5. Great, so that's IVT. Again, IVT, some students get confused because they don't feel like they're doing a lot of work, but this is what IVT says. Your y value is in between the y value of the intervals. So, for example, if this had been 3, it would have been perfectly the same question because 3 is in between 4 and 1. Same thing with like 1.5, 3.5, things like that. So that's how you do IVT. Y values in between the y values of the endpoints. Now for MVT, I like to remember the phrase is calculus slope equals algebra slope. If you wanted to use rates, it's the average rate is equal to the instantaneous rate. So what I do is by MVT, and then I have this number, negative, I find the algebra slope actually. Let's find the algebra slope, because it's algebra slope equals calculus slope, and let's hope and pray that it's equal to -1. So let's see what happens. So we're going to do algebra slope, and what are we going to do algebra slope on? Well, we're going to do algebra slope on velocity, because acceleration, this being a of c being acceleration, v of t being velocity, of course, acceleration is the derivative of velocity. So what we need to do is we need to find the algebra slope on velocity. Again, we're going to use the columns 2 and 5, so it's going to be 2 and 5. So it's going to be v of 5 minus v of 2 over 1 minus 4. Looks like we're going to get, sorry, not, I keep doing slope wrong. So y minus y over x minus x. So it's going to be 1 minus 4 over 5 minus 2. And notice that's -1. The exact number that we want. So again, this is a little bit different than IVT. IVT, all you need to show is that the y value is in between the endpoint y values. For MVT, you need to show that there's some number. Your number that you get for algebra slope is exactly what they want the calculus slope to be. So there's no in-betweeners. IVT has in-betweeners with the y values. MVT, you want your calculus slope to be exactly equal to that algebra slope. But notice that it is. So again, what you do is you sort of repeat their sentence. There does exist an a c such that a of c is equal to -1. So there does exist c where a of c is at -1 and c is in between this interval. So again, this is MVT, IVT. Let's go over it one more time because it is very important. It appears most on every single table for response question. So if you have something weird where you're never finding the time value, you're actually showing that some time exists in some interval, why must this exist? Why must this equation have the solution? What's the fewest number of times this happens, but don't actually find the t's that actually make it happen? That's going to be IVT and MVT. IVT generally is when the function in the table matches the question function. So in this case, velocity and velocity. MVT is usually when the function in the table is, and then you have the given function, and that relationship is a derivative. So the derivative of the given table function is the function in the question. So in this case, we have acceleration. Given was velocity, so we were doing MVT. For example, if this was acceleration and the given was acceleration, that'd probably be IVT because they match. So with IVT, what you do is you show that your y value you want is in between the y values of the endpoints of the interval. Same thing with MVT. MVT, you use the endpoints of the interval, but you use them to construct algebra slope, and you want that value to be the exact same. For both questions, what you do is you repeat their sentence when you conclude. So there's a little bit trickier MVT or IVT questions. For example, right here. So let's think about it. The wording would be, why must there be a C, blah, 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 such that f prime of C equals 1. Again, that's an IVT or MVT question. Looks like we're going to be doing MVT in this question because f prime is the derivative of f of x, and that's the thing in the table. But just keep in mind that when they give you the entire interval, you might not use that entire interval. So for example, if you eyeball algebra slope here, it'll be 4 minus 2, which is 2, over 10 minus 3, which is 7. So it's 2 over 7. That's not 1, but that's still fine. What they're asking you to do is you have to actually examine the table, calculate a few slopes in your head, and just see which two pairs of columns have slope 2. Theoretically, they don't even have to be adjacent, but usually they are. So in this case, again, it's going to be the same as that question with MVT. Calculus slope equals algebra slope. But instead of doing it on the entire interval, or a specific interval that they give you, 2 to 5 in this case, they gave me 2 to 5, I'm actually going to eyeball slope, but it's actually pretty easy to tell where the slope is equal to 1 in this table. Keep in mind that it's going to be for these 2 points here, these 2 columns, because you have 1 over 1 basically when you do algebra slope. So we can start by MVT. Again, we're choosing MVT because it's the derivative of the thing in the table. Then you would say something like f of 9 here. Let's see if I can do algebra slope this time. Over 9 minus 8. This is 5 minus 4. So you end up getting 1. We can write it kind of small. So you end up getting 1. And again, with MVT, you do want that algebra slope to be exactly what they want the calculus slope to be, because that's what mean value theorem says. Then you would, of course, conclude something. So by MVT, because the algebra slope is equal to 1, and that's what you wanted the calculus slope to be, there exists a C in this interval where f prime of C is equal to 1. So again, just be wary that when you're doing these MVT questions, sometimes it's not on the given column. Sometimes you have to choose specific columns. Same thing with the fewest number of times question. So sometimes they ask, what's the fewest number of times that f prime of C equals 0? And this is also an MVT question. Just keep in mind, it is worded weird. They don't actually find you any t values. It's MVT because you have f prime, and that's the derivative of the thing in the table. But keep in mind that when you have the number 0, sort of like when we have the number 1, the number 0 is actually very easy to tell where 2 columns have slope 0, even if they're not adjacent. Because, of course, if you have 2 points and the y coordinates are the same, you're going to be doing y minus y, and that will be 0. So that will have slope 0. So when you're finding slope 0, this is actually a specific form of MVT. It's called Rolle's theorem. But it's very easy to eyeball where things have slope 0. It's harder, for example, to eyeball 2 columns that have slope 1. But slope 0 is really nice, because notice if I do algebra slope on these two, you'll get 2 minus 2. Same thing with 4 and 4. They don't have to be even adjacent. And even if they're not adjacent, they're still pretty easy to spot. So in this case, and like normal for some reason, the fewest number of times will be 2 times. And we'll explain that. So by MVT, again, we're using MVT because it's worded weird. There's some sort of existence, and also we have a derivative. So what we're going to do is we're going to do algebra slope. And again, we chose these 2 pairs of columns because when you do algebra slope on them, because they have the same y value, you get 0, and 0 is a great number. So you get f of 5 minus f of 3, 5 minus 3 equals 0, but that's also this because it's 2 minus 2. Same thing with f of 10, even if they're not adjacent. F of 10 and f of 8. Sort of running out of room here. Sorry that I'm messy. But you get 4 over minus 4 over 2, which is 0 over 2, which is 0. So that's always great. So by MVT, because these two algebra slopes are equal to 0, the fewest number of times where f prime of c is equal to 0 would be 2 times, where of course c is in this interval, c to 10, because we found one. Sorry, let's change that to less than. So we found one of them that's going to be in between here and here by MVT, because this algebra slope of these two columns is 0, and then from here to here, the algebra slope is going to be 0 as well, because they're the same. But basically, let me just remind you a few things to do with MVT, IVT, and then we'll move on. So first off, you know it's an MVT or IVT question when they ask you the existence of a time or an x versus finding an x or a time. Secondly, the general rule of thumb is if the function in the table matches the given question, you're probably going to be doing IVT because it's all about y values. If the function is the derivative, if the question function is the derivative of the function in the table, you're probably doing MVT because MVT is remembered as calculus slope equals algebra slope. When you're doing IVT, what you want to do is you want to show that the given y value or the question y value is in between the y value of your endpoints. So here 2 is in between 4 and 1. Then for MVT, what you want to do is you want to show that the calculus slope, what they want the calculus slope to be, is equal to whatever that algebra slope is on that interval. So what you actually do is you never actually find the calculus slope, you actually find the algebra slope and verify it's that derivative. And then also finally, sometimes you don't use the columns that are given to you because they give you the entire interval. So like, for example, 3 to 10, they give you the entire interval. So you have to sort of eyeball slopes. But also, that question is asked when you have slope 0, but slope 0 is pretty easy to find because they have the same y values. When you're writing your sentence, I like to either write by IVT or by MVT, and then I do my justification, and then I conclude with their statement that they want me to prove. One more thing is that IVT requires a function to be continuous because you can't lift up your pencil so that these y values do exist. Sometimes people like to add that to their justification. And also for MVT, you want it to be differentiable because you want to be able to take derivatives. And of course, differentiability implies continuity. So continuity is a requirement for MVT. These two theorems are always hold. So there's some weird questions where they're like, why does MVT not why does this weird statement not disagree with MVT? And that's usually because the function is not differentiable, so you can't even apply MVT. But if you sort of focus on what we talked about earlier, when to use MVT, IVT, how to choose between MVT or IVT, and then how to run each one, then you should be good with MVT, IVT, even if they're kind of weird because they're existence theorems. So that's our two main things we talked about so far. We talked about average and derivatives, and we talked about MVT or IVT. The next huge thing we need to talk about is Riemann sums. So before we start, let me just focus on two things. You have to know how to do all 4 types of Riemann sums. So you need to know how to do left, right, trapezoidal, and midpoint. The second thing you want to know is that sometimes the Riemann sum is not the answer. So after we practice Riemann sums, we'll see that sometimes you have to do an additional step after you find the Riemann sum. Either maybe dividing for average or adding for a fundamental theorem of calculus, or being careful with like overestimate and underestimate on total distance. So let's get on with it. So again, you need to know how to do the 4 types. That's the main thing. You need to know how to do left, right, trapezoidal, and midpoint. And they're not too bad because, of course, they're just adding and multiplying numbers. You just have to determine which numbers to multiply. Before we go on, I forgot to mention that if you're struggling with MVT or IVT, or if, for example, you're struggling with Riemann sums, we have separate videos on our channels for that if you want to watch them. But let's practice left, right, and trapezoidal first. So we're going to use this table. So the key thing by far is that when you're doing Riemann sums, you're always finding the base of some shape, either a rectangle or trapezoid, and then the height is determined by f value. So always the difference in the x's is the base of the shape. So you'll see that when we do L5, R5, and T5, left, right, and trapezoidal with 5 subintervals, you'll see that certain numbers repeat. So for example, let's practice L5. So it's going to be the difference in the x's or the t row, the top row, because that's going to always be the base of the shape, no matter if I'm doing left, right, or trapezoidal. So in this case, my first rectangle's base is going to be 3. And then determine the y value, the height of the rectangle, it is the y value, the function value. So if you're doing left, you would choose this number. If you're doing right, you would choose the y values of the right endpoint. And then if you're doing trapezoidal, you do the average of these two. So in this case, it'll be 3 times 2. Because it's 3 difference in the x's times a different y. Same thing in the next one. Difference in the x's, so 6 minus 4 times a different y. So it's going to be 2 times 0. And then I'm going to keep going, of course. Difference in the x's, like normal. So it's going to be 4. And then we're going to choose the left y value in this pair of columns. So it's going to be negative 1. It's okay. So it's going to be 4 times negative 1. Same thing here. 1 times 3. And then finally, 2 times 5. But again, always difference in the x's times the y. So it's this times this. This times this. This times this. This difference times this. This difference times this. And of course, when you actually find it, you'll want to be careful with numbers. These don't look too bad, so we can probably simplify it. It's going to be 5 minus 4, because this is 0, so it's 1. 1 plus 3 is 4. 4 plus 10 is 14. But again, usually students, once you master the concept of Riemann sums, you actually prefer those kind of questions because, again, all you're doing is adding and multiplying numbers. You just have to determine which ones to add. Let's do R5. So for R5, it's, again, still the difference in the x's. So notice when we do this rectangle, it will still be 3 in the front. So this 3 matches this 3, not by coincidence, but it's always going to be like that. The bases are always the same. Then we multiply by 2 for the left, but this time we're going to multiply by 0 because 0 is the y value of the right Riemann, this right interval. The interval is from 1 to 4, so we're taking the function value at the right endpoint, which is 4, so it's f of 4, which is 0. So it's going to be 3 times 0. Then, for our second rectangle, again, it's the difference in the x's, so this is why this is 2, and this 2 matches this 2, because it doesn't matter for left or right. For left, we chose 0. For right, we're going to choose negative 1. Going on, it's going to be 4 times the 3. Moving forward, it's going to be 1 times 5. And then moving again, difference in the x's times the right endpoint. So it's going to be 2 times 1. So keep in mind the first number in all of these products that we're adding up was the same because we had the same base. 3, 2, 4, 1, 2. What's changing is, are you choosing the y value of the left endpoint or the y value of the right endpoint? And that's how you do Riemann sums. Keep in mind when we were doing L5, we didn't use this 1 number at the end because 1 is not the y value of any left intervals. So let's find R5 real quick, and then we'll do trapezoidal, which is a little bit trickier. So it looks like it's going to be minus 2 plus 2 at the end, so those will go away. This goes away as well. So it looks like it's going to be 12 plus 5, and that's 17. So trapezoidal is the trickiest one, but again, it's not too bad. It's the same sort of process. It's always the difference in the x's, so that's why it's 3, just like these were 3. And then instead of choosing 2, which we chose for left, or 0, which we chose for right, we are going to do the average of them. And of course, the average of two numbers is you add up the numbers and divide by 2. So it's going to be 2 plus 0 over 2. Now we're going to do the second one. So it's going to be always the difference in the x's. It's going to be 2 times 0 plus negative 1, that's fine, over 2. Just remember, something plus something over 2. We might run out of space here, but I don't think it's going to be too bad. We'll just go down. It's going to be, looks like the next one is going to be 4. So it's still the same number, 4 times, and instead of choosing negative 1 or 3, we're going to do the average of them. Also, I don't like taking the average as I'm doing the table. You might be better at math than I am. I like to write this out, and then later on, I might multiply fractions or something like that. So in this case, the last two are 1 times 3 plus 5 over 2. Like, again, I could probably do that average in my head, but I like to be careful. And then finally, again, one last time, difference in the x's times the average. So it's going to be 2 times 5 plus 1 over 2. So we can probably add up all these because it's actually not too bad. So this one, we'll just go over here. It's fine. This one's going to be 3 because it's 2 over 2. These 2's cancel, so it looks like we're going to have negative 1. These 2's cancel. Or if you want, actually, negative 1 plus 3 is 2. 2 over 2 is 2, so this is just 4. This one is 8 over 2, which is another 4. And then finally, this one is 6 over 2. That's 3 plus 2 is, times 2 is 6. So this is what we're going to add together, 10, 17, 16. So this is T5. But again, if you've never seen this before, it's not too bad at all. It's always the difference in the x's times different y values, depending on if you want to choose the left y value, the right y value, or the trapezoidal. Now, the last sum couldn't be done in this table because for midpoint, you do need to know the midpoint values. But again, it's the same thing. Keep in mind that midpoint is a little bit weirder than left, right, or trapezoidal because instead of using pairs of columns, you use sort of triads of columns or trios of columns. You're not grouping columns into pairs by twos. You're grouping things into threes. So, for example, in this case, we would group it from 3 to 9 and 9 to 15, as opposed to 3 to 6, 6, 9, 9, 12, and 12, 15. Then it's still the same thing because it's still the base of that rectangle will be the difference in x's. So it's still going to be 9 minus 3. Be careful, it's not 6 minus 3. This entire base goes from 9 minus 3, so it's going to be 6. And then instead of choosing the left endpoint, which would be left Riemann sums, or the right Riemann endpoint, which would be right Riemann sums, we were going to do the midpoint value, the y value of the midpoint. In this case, it is 6. So that's why they have to present it in this way, because they have to give you the function value for the midpoint. So it's going to be 6 times 2. The next rectangle is going to be 15 to 9, so that's 6 again. And then we're going to choose the midpoint value again, so 6 times 3. So notice midpoint's a little bit weird because you're not including basically every other number because those are not midpoint y values of midpoints. But again, this is how you do this guy right here. This is going to be 6 times 5, which is 30. So again, you have to know how to do these Riemann sums. Left, right, trapezoidal, midpoint. They come equally often, maybe 25% chance for each one. And again, they're not too bad to know because they're just multiplying and adding numbers. You just have to know which ones to add, and then you will be good to go. But what I like to tell my students is that sometimes the Riemann sum is not the answer, meaning that you find the Riemann sum, but the Riemann sum is not your final answer. You either have to write a sentence about it, or you might have to do an additional step, a simple arithmetic thing to get to another thing. So remember that Riemann sums, so we can just write in this random space here, but Riemann sums are used to approximate integrals. So used to approximate like f of x, if the function is f of x, so it approximates this. So for example, if you're just finding the integral, that means the Riemann sum will be the answer. But if you're using something that involves an integral but isn't strictly an integral, you might have to do an additional step. And we'll see that here. So the first thing actually isn't like this, but what we're going to do is we're going to do a quick left sum, and then we're going to, if we know that the function is increasing, 3, 4, 8, this has to be given in the table. We're going to determine whether this approximation, because remember, Riemann sums approximate integrals, we're going to determine whether this approximation is an overestimate or an underestimate of the actual integral value. So first let's do this quick left sum. So the L3, or it's actually L2 because there's only 2 pairs of columns. So L2, remember it's the difference in the x's, so it's going to be 3 times, and then we're going to choose the left point, so 3 times 3. And then this will be 4, difference in the x's times the y value, which happens to be 4, so not the best question, but that's fine. 9 plus 16, I believe, is 25, because it's a 3, 4, 5 triangle. None of that matters. So this is the L2. Again, not the hardest thing, but you might have to justify whether this approximation. So this would be approximating the integral of f of x over this endpoint. So for example, it'd be 2 to 9. So 2 to 9. So we are approximating this integral, and the question is this approximation, is 25 over or an underestimate of this integral? Well, what you do is you actually don't look at the left Riemann sum at all. You just think of the words left and increasing. So what I like to do is I like to draw any increasing function. It can be concave up or down. I like to fix an endpoint, and I like to just draw a Riemann sum. So it's a to b. I call it a to b. You can just call it, you don't even need to label it any. But the left Riemann sum means that this endpoint, a, will be, the y value of that will be touching the curve. So in this case, you draw it, so you go up, take the left endpoint, go up to the function. That's how tall your rectangle is. Draw the rectangle, and then just notice, is this under or over the actual function? Because that will be the integral, that's the area of the curve. So in this case, it's under. So if you have f increasing and you have a left sum, that's an under. So that's one of the underestimate, overestimate questions that they like to ask. Again, that would be an additional thing. They would ask you to first find the approximation, and then later on you would say, well, this is an overestimate, or whether this is an underestimate. In this case, it was under. For example, if you were doing a right sum and increasing, it would be over because the function would be this tall, and then everything would be reversed and a decreasing function. There are only 4 possibilities, but I don't memorize them all because I can just draw these simple little pictures. But again, just focusing that sometimes the Riemann sum is not the full answer. Same thing in this case, as we talked about, sometimes these questions are particle motion questions. So in this case, we have sort of fundamental theorem of calculus thing. How do I know it's fundamental theorem of calculus? Because they give me something about the derivative, which is the position, and then they give me an initial point. So that's the lingo, and that's the conditions to do fundamental theorem of calculus. When they give you something about the derivative, either a graph or a table or a function laid out, and then they give you an initial point, f of something equals something, the initial position is this, things like that. Again, this is a particle motion question. You see fundamental theorem of calculus and those particle motion free response questions that I referred to if you want to check out our videos on those. But I set up fundamental theorem of calculus in always the same way. So it's going to be s of the given. So initial means time is equal to 0, so be careful with that. But it's s of the thing we want, s of 6, equals s of the given. So s of 0, I'm just going to write 5. And then to set up the integral, I always put my given time on the bottom, my want time on top, because that's how you do fundamental theorem, and then it's bt. So you'll set up fundamental theorem of calculus in a multitude of ways on the AP exam or any assessment. Keeping in mind that there's a lot of ways to actually do this integral. You might take antiderivatives, you might use a calculator. In this case, we're going to approximate with a Riemann sum. In this case, a right Riemann sum. So let's do that over here. So it's going to be 2 times 3, because it's always the difference in the x's or the t's, times the y value. Same thing here, 6 minus 2, difference in the x's or t's, times 4. So it's going to be 4 times 4. That's going to be 6 plus 16, that is 22. But keep in mind, this is what I want to tell my students as much as possible, even when they get super annoyed with me. This will not be the answer because we have to add the 5. So at the very end, the actual answer is 27. Again, the Riemann sum is only approximating the integral. It doesn't find the integral itself. So when you find a Riemann sum, that will be your approximation of the integral. So if you need to add something in the front, you do have to add. So this is my example. The Riemann sum is not the answer. You have to do one additional step, adding because of fundamental theorem of calculus. Same thing with a very common question, which is average temperature. So we're doing average temperature with trap, meaning trapezoidal. So what's the formula for average temperature? The formula for average value, it's different than average rate that we talked about earlier. Average rate is usually the algebra slope. But average value is 1 over b minus a, the integral of that thing. So whenever they don't list out the integral that I want to approximate with the Riemann sum, I like to list it out because I have to it'll help me later in the future to determine, is that the answer or do I need to multiply or add a certain number? So in this case, again, what is average temperature over t equals 2 to 7, of course? It would be 2 to 7 temperature. And then you need to put the number in the front. So you put 1 over 7 minus 2. So again, another small thing. The Riemann sum will be this, and then we'll multiply by 1/5 in the end. And then we can quickly do this Riemann sum. So in this case, keep in mind that it's always the difference in the x's still, or the t's. So it's going to be 3 minus 2, which is 1, times 1 plus 4 over 2, because it's the average of these two. You don't choose either one. Same thing with this. It's going to be 4 times 4 plus 3 over 2, the average of the y values. We did that earlier with this trapezoidal. So it's going to be 4 plus 3 over 2. And then we are going to add this up. So it's going to be, looks like it's going to be 5 halves plus, let's not actually cancel these out because we need to treat it as a fraction. So it looks like it's going to be 7 times 4 is 28 over 2. And then finally, 5 halves plus 28 halves is 33 halves. Hopefully you can see what I'm writing here. Keep in mind though, again, this 33 halves, it's so easy just to write this as the answer and move on. We all know you're super excited to do calculus all the time, but of course you do need to remember multiplying this 1/5, and that's the average. So in this case, it'll be 33 over 10. So what we're focusing on, especially these are the two main questions. Sometimes the Riemann sum is not the answer. Sometimes you have to do an additional step. Finally, again, some of these questions are in particle motion, and oftentimes you're not finding the integral of velocity, the thing you're approximating, the integral you're approximating. Sometimes you're actually doing the integral of the absolute value of velocity. So let's review a little bit of particle motion. So when you have v of t, that's velocity. When you have the absolute value of velocity, that's speed. When you take the integral of velocity, that's just the total displacement, but when you do the integral of speed, that's total distance. So oftentimes they'll ask you to interpret it. This is the total distance. We're going to practice interpretations in a second here, but we can practice right now. So it'll be the total distance. Whenever you have an integral and you're interpreting an integral, you always want to include the endpoint. So from t is equal to 2 to 10. Of course, the units of total distance will be a distance unit. So whatever the velocity is, you would lose the time. We talked about how when you take a derivative, you gain a time period in the denominator, but when you take an integral, you lose the time. Just think about meters per second squared for position, velocity, and acceleration, respectively. So again, this is total distance. You've seen questions where it's average velocity. Average velocity would be somewhat like this. 1 over b minus a, the integral velocity, where you would do the Riemann sum for the integral velocity, and then you would multiply by the number in the front, 1 over the length of the interval. So in this case, we're doing total distance. So this is also a very tricky question. We already did the interpretation, so we're good to go. Let's do a midpoint. Sorry, this line was supposed to be for this table right here. Let's do a midpoint for this guy. So again, it's going to be 4. It's grouped in 3, so each one is length 4. So it's going to be 4. And just be very, very careful. Notice that we're not actually doing the integral of velocity, that's total distance. We're doing the integral of the absolute value of velocity. So what we need to do is we need to not treat this as -3. This is the y value of the midpoint, but we want to take the absolute value of that. So we're going to actually treat that as 3. So again, all the velocity values that are negative are actually positive because you're doing the integral of speed, not the integral of velocity, so that you can find total distance. This one doesn't really matter. It's going to be 4 times 4. So in this case, it's 4 times 3 plus 4 times 4. That's going to be 4 times 7, which is 28. But again, just be very careful. When you're integrating the absolute value of velocity, you need to treat this as positive and not negative. Of course, we didn't use these 3 numbers because we were doing midpoints. These are not midpoints of any of these intervals. So again, be very careful. That's the same thing when velocity is given as a graph and you're finding the integral of the absolute value of velocity. So you're doing total distance. It's the same idea. When you're considering that integral, which you'll be doing because of areas, because it's a graph, every area that's negative that you usually, every area that's under the curve that you usually treat as negative, you'll count as positive. So again, let's recap Riemann sums really quickly, and then let's go to those interpretations. So you have to know how to do Riemann sums, left, right, trapezoidal, midpoint. It's always the difference in the x's times different y values, either the left y value, the right value y value, or the average of the y values for trapezoidal. Midpoint, you do the y value of the midpoint. Then just remember that sometimes the Riemann sum is not the answer because the Riemann sum is only used to approximate an integral. So for example, they might ask you to do decreasing questions with overestimate, underestimate. For those, you just draw a picture. Another common question they like to ask is either fundamental theorem of calculus or average, where they'll ask you to find the Riemann sum, and that might be a point or two, but then they'll give you an additional point for the real correct answer, which requires you to manipulate it some sort of arithmetic operation, either dividing because of average here or adding because of fundamental theorem of calculus. Finally, if you're finding the integral of the absolute value of velocity and you're using a Riemann sum to approximate that, you want to use every single velocity is positive, actually. So we're almost done, even though this video is getting quite long. So let's talk about interpreting. So interpreting is, again, one of the steps that people have the most trouble with because it's sort of the theoretical side, where you're not just like doing math and you're like just plugging in numbers and stuff, but you have to like interpret. So in this case, r prime of 4, we already did this before. What we're going to do is we are just going to approximate the algebra slope. remember you choose these two columns. So it's going to be, give me a second, r of 5 minus r of 3 over 5 minus 3. So this is going to be 2 minus 6. We're choosing these columns, of course, because 4 is in between 3 and 5. So it's 2 minus 6 over 5 minus 3, which is negative 2. So what's the interpretation of this? Well, let's see what r is. R is the rate of temperature of some temperature function, t of t. Keep in mind that it doesn't have a derivative, but it's still a rate, because I'm saying it's a rate. The units of this is in Celsius per minutes. So again, what's going to be the units of this? Well, the units of this is, we're going to gain a time period. It's going to be Celsius per minute squared. And then what's the interpretation? Well, the best interpretation in my books is if you have something about a derivative, you want to talk about increasing or decreasing. Because f is increasing when f prime is positive, f is decreasing when f prime is negative. So for example, in this case, I would say the rate of change of temperature. So notice we're actually talking about the rate of a rate, which some people get confused on, but it's basically acceleration. But the rate of change of temperature, and then if it's this number right here, I'll say is decreasing because it's negative. 2 degrees Celsius per minute squared, or minute per minute. And then they like to for you to allude to whatever point you're doing. So in this case, it'll be at t equals 4. So that's the interpretation for a derivative. Just something is increasing or decreasing at this number. These are the units. We talked about this one before. So this approximation is going to be, or this interpretation is going to be average, because it's 1 over b minus a times the integral. So let's practice another left sum one more time. So remember that again, we need to multiply by this 1/6 at the end. It's going to be 3 minus 2, because it's always the difference in the t's. 1 times the left value, 1 times 3, 2 times 6, 3 times 2. We're going to get 1/6 times 3 plus 12 plus 6. And then we are going to add up all these. And then, of course, we're going to remember to divide by 6, because sometimes the Riemann sum is not the answer. So in this case, you're going to get 18 plus 3 is 21. 21 over 6 is the same thing as, I believe, dividing everything by 3, 7 over 2. So that's going to be our... So that, again, that's not anything new. That's a Riemann sum left where we multiply because we're finding average. But what's the interpretation? Well, I just gave it away. It's going to be average. Just keep in mind whether it's average rate or average, just strictly average. In this case, it is the average value of whatever this is. This happens to be a rate, so I'm going to call it average rate, but it's always average. So it's 7/2 is the average rate, whatever your function is. So if this had been t, it would be average temperature. In this case, it's r, so it's average rate of temperature. Again, they like you to allude between what numbers you're going to. So from t equals 2 to 8. We should talk about units. So the average of anything has that same units. So in this case, it is going to be Celsius per minute. Average temperature would just be in Celsius because it is a temperature. In this case, we're doing a rate of a temperature, so it is matches the same units. If you're thinking about it with integrals and dividing and stuff, when you take the integral, you would lose a time period, so you'd have degrees Celsius, but then you're dividing by a time interval, it's divided by 6, so that's why you reintroduce the same units. So it would be, only this would be degrees Celsius, and then you would have divided by time, so then you would be left with what you were started off with, degrees Celsius per minute. So again, when we took a derivative, we gained a time. When we did average, we got the same units. And then for integral, as we'll see, you lose a time because you're taking just the integral, no number in the front. So in this case, we can't do this question, so we're going to write r prime of t instead. So sometimes they just ask you to find this integral of r prime of t, and that's very easy. All you do is you just take the integral using fundamental theorem of calculus. So what's the antiderivative of r prime? That's just r. So it's going to be r of 8 minus r of 2. How in the world do you find these numbers? Well, it's just in the table, so this is a very easy question. It's 4 minus 2. That's going to be 2. And then the question is, what's the interpretation? So again, this was fundamental theorem of calculus. What's the antiderivative of r prime? It's r. Plug in the top, plug in the bottom, subtract. Use the values in the table to do that. Sorry, I didn't use the right values, but it's 4 and 3. So 4 and 3, which is 1. So And the easiest question, I couldn't read the table. Sometimes reading the table is actually kind of difficult. Some students definitely miss that, so just be aware of that. But in this case, what's the best interpretation? Well, if you've seen our free response question videos, our very first series, it's called accumulation free response questions. Those include rate in or rate out questions. But basically what happens is if you have the integral of a rate, when you do fundamental theorem of calculus, the integral of a rate is the net accumulation or the net change of whatever the rate was of from your time period. So in this case, what is 1? I like to always use the word change. So what it's going to be is whatever your R is. So in this case, it's rate of change, but keep in mind if it was T, it would be T. But in this case, it's the 1. So the change and whatever R is, the rate of the temperature, was 1 degree Celsius per minute. So again, this is R's, so this is going to be degrees Celsius per minute from T equals 2 to 8. So that is my interpretation. So let's recap interpretations. When you have a derivative, it's going to be something, whatever it is, R in this case, is increasing or decreasing at this time. When you're doing 1 over b minus a times the integral, it's going to be the average of whatever is in the integral. And then when you're doing fundamental theorem of calculus, the integral of r prime. So here the integral of r prime is just r. It's going to be the net change of that thing. So for example, if this were integral of r and this had been t values, you would still do the same thing. The antiderivative of r would be t. You'd plug in top minus bottom. You would do t minus that number. So for example, t of 8 minus t of 2 maybe. You would find those numbers using a table if this were t instead. And then the interpretation would be it changed whatever 5 degrees from t equals 2 to 8, whatever that difference is. So these are the main interpretations. Again, if you practice them a bunch, you won't get confused about them, and you'll be able to get those small little points here and there. So finally, the 3 things we talked about, or maybe the 4 things we talked about, usually cover the majority of these table free response questions. But there are some questions that are sort of miscellaneous. Basically, they might introduce another function in part D, for example, or they might so usually these questions go outside of the table, and you might use a calculator or something when you're dealing with these things. But say you're given a random function that has nothing to do with the table and you want to find a rate. Well, that's just going to be the derivative, so just keep in mind. Usually you have a calculator, so you can just use calculator derivative at a point. These questions are very easy. Usually people get them. Same thing as if you wanted to see if something is increasing or decreasing, as we said before. What you want to do is you want to find the derivative, see if it's positive or negative. So if they say, here's this new function. It doesn't have anything to do with the table, but here it is. Let's call it W. Do you want to see where W is increasing at 4? So all you would do is you find W prime of 4. If it's positive, it'd be increasing. If it's W prime of 4 is negative, it'd be decreasing. And you probably just finding W prime of 4 with a calculator derivative at a point. The reverse is, of course, when they give you a rate instead, and they give you an initial point, and that's when you use fundamental theorem of calculus. So, for example, they'll say the initial temperature is 50 degrees Celsius. Find the temperature at t is equal to 8 or something. And then they say, I'm going to give you the derivative of the temperature, whatever it is. They'll list it out. Again, this is sort of the conditions for fundamental theorem of calculus. An initial point, some derivative thing, and then they want you to find the temperature or the antiderivative at another point. And I always set it up in the same way. What I want, t of 8, it's always the given y value, the given function value, so it's going to be 50. This is t of 0. And then I always put my given t value on the bottom. In this case, it's 0 because it's the initial time. And then I put my want t value on the top, my want x value or t value, 8. So this is the setup of the fundamental theorem of calculus. And then what goes inside the integral, it's the derivative. And then usually you're typing this in a calculator as well. Same thing if, as we said, if this were all particle motion questions, initial position, here's the velocity. It doesn't have to do with the table, but here's the function for the velocity. Now find the position at another time. That's fundamental theorem of calculus. Finally, the main question they like to ask in these miscellaneous levels are related rate questions. Of course, if you want to practice related rates, this is probably not the time to do it. But we do have, sorry, my sort of light went out, but I think it should go back on, maybe. We will see. I don't think it should be a problem with this last question, but hopefully you can tell what's going on. So we have related rates. So again, with these related rate questions, here's my light, so that's great. But for these related rate questions, we have videos on related rates if you want to check them out. But basically for related rates, you want to focus on three things. You want to locate the function, which is often given. You want to take the derivative of whatever function you have. And keep in mind that this is going to be some sort of situation where time is the big variable. So when you're taking this derivative, you have to do implicit differentiation. Meaning that every single variable, including x, might have to use implicit differentiation because the actual variable that the independent variable is time. So for example, you might have some function like f of x is equal to x squared, but and you're finding related rates and things like that, but x is a function of time, like x represents something that's changing with respect to time. So when you take that derivative, it's not just going to be 2x, the derivative of x squared, it's going to be 2x times dx dt. So this is the key step. You have to implicitly differentiate everything. Time won't actually be in the one of the variables, it's usually another variable, but all the variables are in terms of time. So again, when you're taking derivatives of those things, you need to remember that. Thirdly, once you take the derivative, it's usually pretty easy. You just start plugging in all your values, all your givens, to find whatever derivative you want. So you might have like 7 variables or something, but they usually give you 5 of them. What they do is they usually don't give you one of them, just as a tease, I guess. And what you do is if you need one last variable to plug in to find the variable you want. So like there's x, x prime, y prime, z prime, because everything needed primes. But they give you like x, y, and z. Or sorry, they give you x, y, x prime, y prime, and you're finding z prime, so you still need z. What usually happens is you use the locate function, the original, to find that last one. Sometimes it's using the Pythagorean theorem, for example. But if you have one last variable, use the locate function, the thing you're doing the derivative of. Use original function. Again, especially in the latter half of this series, this video series, as we do table for response questions, we cover some of those related rate questions. But again, the keys to remember are locate something that's usually given. The main mistake is taking the derivative where everything needs prime. So even if you're taking the derivative with quotient rule or product rule or chain rule or something like that, you need to multiply by dx dt, dy dt, dz dt, dA dt, whatever it is. Usually, because all these are respect to time. Then the easy step is to start pulling in stuff, and then you might have one last thing to do and one last variable, and you use the original. So that's it for table for response questions. This has been quite a long video, of course. This has been almost an hour. Let's just review the main questions. The main questions being approximated derivative or average rate using algebra slope on an appropriate pair of columns. MVT, IVT, it's a weirdly worded question. MVT is calculus slope equals algebra slope, so that's when you usually do that, when the want question is the derivative of the given question. IVT is usually when they match because you're dealing with function values. For IVT, you show that one value is in between. Whatever y value you want is in between the y values of the givens. For MVT, you show that the algebra slope is equal to what they want the calculus slope to be. Then you justify. Keep in mind that you might not be doing the interval that's given. You might be have to eyeball certain slopes and things like that. And also for MVT, you might have this fewest number of times or where's the derivative equals 0. But that's pretty easy because they have the same y values. That's Rolle's theorem. Then we really focused on Riemann sums. We knew how to do each one, left, right, trapezoidal, midpoint. Again, the key is it's always the difference in the x's times different y values. Left, right, the midpoint value, or the average of the left and the right for trapezoidal. Then we talked about how the Riemann sum is not always the answer. For example, when you're doing fundamental theorem of calculus, or when you're doing average, you might have to add something or multiply by something. Same thing with the overestimate, underestimate question. You have to interpret that outside of the Riemann sum because the Riemann sum is only the integral. And then when you're doing this total distance thing, remember that every single value in the table is actually treated positive because this is total distance, the integral speed. Then we talked about interpretations. Derivatives are increasing or decreasing. 1 over b minus a times the integral is average. And then finally, when you apply fundamental theorem of calculus using the table, that'll be the net change or whatever it is. Then the miscellaneous stuff, take derivatives if necessary if you want to find rates. Use fundamental theorem of calculus if you're given rates and you want to find the initial function. And then finally, for these related rate questions, which we do have examples for in our videos on related rates, of course, but also throughout the series as we go from difficulty 1 through 10. Keep in mind that everything needs implicit differentiation. Use the original function if you have one less variable to plug in. So now that we hit the hour mark, I'm going to be going soon. Again, we rush through all these really fast. Again, this is one of the most important free response questions. This is one of my favorite ones because you're not really doing much math. You're just multiplying and adding numbers and dividing and maybe applying MBT or IBT or whatever. So you want to get really good at them. You want to have free response questions on the AP exam, for example, that you know you'll do well on, and this could be one of them, table free response questions. So what you want to do is, if you want a lot of practice, that's what we've created for you on this channel. We want to help you guys out as much as possible. So we start at difficulty 1 and we do all these typical questions. Approximating derivatives, Riemann sums, MBT, IBT. Then we slowly progress. Every other one is a particle motion question because particle motion question appears so often, but we'll see eventually a rate in, rate out question and things like that also in these questions. And then we go harder levels. So we do some sort of hard integrals maybe when it's outside of the table, or we might do those related rate questions that are very tricky. So again, we feel that if you watch this video series, it will be a good practice for these very important free response questions. And of course, we do this for every single one. So if you wanted to practice more particle motion questions, check out those videos. The accumulation free response questions that we alluded to before, check out those. We also have individual videos on each topic if you want. For example, MBT, IBT, Riemann sums, and related rates. So check those out if that would help for you. But again, hopefully this has been useful. I hope to see you in those videos from difficulty 1 through 10. Until then, thanks again for watching, and goodbye.